This is Thermochemistry Part 6. This is Heats of Reaction. We're going to start off by actually looking at another molar heat. We're going to look at molar heat of solution, and this is indicated by delta H, solution, and this is the heat absorbed or released by 1 mole of solid dissolving. So, for example, if we take calcium chloride and we put it into water, it dissociates into calcium 2+ ions and 2 chloride ions. And at the same time, it heats the water up. So here's a problem that we're going to work. The question is, how much energy will be released by dissolving 2.0 grams of calcium chloride in 200 mLs of water? And we're given the dissociation equation right here. And we're told that the heat of solution is negative 82.8 kilojoules per mole. We can read this as 82.8 kilojoules are released for every 1 mole of CaCl2, calcium chloride. So that's how that's read. Now, I've taken care of the sign because since we're doing released, that makes the negative sign disappear. Now, a quick question here. Since we were releasing heat, is this reaction endothermic or exothermic? Well, remember, if we're throwing heat off, it is an exothermic reaction. So this is an exothermic process. Let's go ahead and solve this problem. We're given 2.0 grams of calcium chloride. So that's our given. And we're looking for energy. So let's see what kind of units we should use for energy. So this is energy. We look over here, and our heat of solution is given to us in kilojoules. So let's find kilojoules. So here we go. We have 2.0 grams of calcium chloride. We need to get over to kilojoules. Here's a conversion factor for us, but we need to get to moles in order to use this conversion factor. So we're going to have to convert to moles of calcium chloride. So we're going to bring grams of calcium chloride down, and we're going to convert that to moles of calcium chloride. If you calculate the grams of calcium chloride in 1 mole of calcium chloride using the periodic table, you'll figure out it's 110.98 grams. So we're out of grams. Let's go ahead and cross those out. We're over to moles now. So we're now in shape to use this conversion factor. So if we have 1 mole of calcium chloride, that will produce 82.8 kilojoules of heat. So the moles of calcium chloride are going to cancel out. We're going to multiply everything on the top, divide through by the bottom, and if you take significant figures into account, your final answer will be 1.59 kilojoules. Put a box around it so that I know that you are done. Let's take a look now, instead of dissociation, at an actual chemical reaction. So thermochemical equations are balanced equations showing heat changes. And here's an example here of the chemical equation for methane burning. So this is methane combusting in the presence of oxygen. It produces CO2, water, and 890.4 kilojoules. So our delta H, because we are producing energy, it's an exothermic reaction. The delta H for this reaction actually has a negative sign. It's negative 890.4 kilojoules. What we're going to do now is draw what's called a reaction coordinate diagram for what's going on. And on this axis here, we're going to have energy. And in specific, this is going to be heat content, so it's H. So this is energy. And then this axis here is the actual reaction coordinate. We're going to have reactants. And they're going to make products. as we go across this diagram. So let's say we start off with the heat content of our reactants here. So this would be CH4 and oxygen together, the two oxygens. They are going to react. As they react, they're going to throw heat off. They're going to release heat. So the final products are going to be lower in energy than the reactants. So this would be the CO2 and 2 water molecules here. So we've dropped in energy here. So if we were to indicate delta H on this diagram, it would be the distance from your reactants down to your products. So you can see that it is a negative sign for delta H. We have lost heat. So this system releases heat, or produces, same thing. So the delta H is negative. And the reaction is a classic exothermic reaction. So let's label this up here. This is any exothermic reaction is going to look very similar to this. The products are going to be lower in energy than the reactants. So the reactants are higher in energy, the products are lower. Now, notice if we look at this distance from here to here, and we compare it with this distance added to this distance, they are exactly the same. And that is because we must follow the law of conservation of energy. This says that energy is neither created nor destroyed during a chemical reaction nor a physical process. If we have energy, it's going to be present either as work, as heat, or as stored energy. So this here is stored energy. So we have this distance is still stored energy. And this distance here was the heat that we lost to the universe. So the law of conservation of energy says that the heat in the universe plus our system has to stay constant. So this was lost to the surroundings. This stays in the system. Let's take a look at gasoline as an example. Gasoline, when we put it in the car, we get work out of it. And the work that we get is the distance that that automobile takes us. If you put your hand on the hood is hot. You don't want to touch the exhaust pipe, that's also hot. So some of the gasoline's potential energy is converted to distance, some of it is converted to heat, and then some of it still stays as stored energy because we have CO2 and H2O exiting out of the tailpipe, because this is a combustion reaction. Let's take a look at a second reaction. This time we're going to be looking at baking soda. That's what the sodium hydrogen carbonate is. So when we put that in cookies and we put it in the oven, so we're putting heat into the baking soda, we make sodium carbonate, H2O gas, and CO2 gas. It's these gases that make the cookies fluffy. Since we're putting heat in, this is an endothermic reaction. We're going to have a positive delta H, so it is positive 129 kilojoules. And let's draw the reaction coordinate diagram for this one. So again, this is heat on this axis, and we're going to use joules. And then we're going to have reactants going to products. And I'm just abbreviating it R and P. So let's put our baking soda right here. So this is our sodium hydrogen carbonate. It's one of your polyatomics. And this time we're putting heat in, so we're going to have to add heat. It's like going up a hill. You've got to add energy. So we're going up. So going up. We've got a little dashed line showing our path. And here we are going to have our various products. So I'm just going to write products in rather than writing in all the chemical names. You can see them up there. There's all your chemical names. So this is products. This time we had to put in heat, So our delta H is the distance straight up between our reactants going to our products. So we have a positive delta H. In this case, the system is absorbing heat. So the system absorbs heat, so delta H is positive. So this is a classic diagram for an endothermic reaction. Anytime your products are higher in energy than your reactants, you have an endothermic reaction.